So now that we have a chance to talk about what the common fork join pool is and roughly how it works, I'm going to talk now about how to configure it. And we'll see that there's a couple of different ways to configure certain properties, certain parameters of the common fork join pool. Now, keep in mind that the overall goal of the fork join pool mechanism or the framework in Java is to give you very few knobs to turn because they're trying to sort of auto-optimize everything without you having to worry a lot about it, which is good. However, there are times when you need to control stuff. So let's take a look at some motivating use cases here. And we'll start by talking about the default size of the common fork join pool. So if you go into Java and you call ForkJoinPool.getCommonPoolParallelism, it'll return to you the number of cores that the common fork join pool will use, or the number of threads, which equates to the number of cores that the common fork join pool is going to use by default. And if you have a quad core processor, one that has 4 cores, then the common pool parallelism level is always 1 less than the total number of cores. And that may seem a little non-intuitive at first, but we'll explain why that is in just a second. So what happens here is when you use parallel streams, there's actually the calling thread. So the calling thread, which is a thread that probably you created, either you created it because you spawned a thread explicitly or the system created the main thread for you. There's some thread that the stream is running in where you're running your terminal operation. And that thread, that calling thread, is borrowed by the parallel streams processing framework. So the calling thread plus 1 less than the total number of cores known to the execution environment equals the number of cores on the machine. So what basically is happening is by default, threads, the number of threads that'll be used to execute a parallel stream will be equal to the number of processor cores known by the underlying execution environment, the JVM, for example. But the actual size of the common fork join pool is always 1 less because the calling thread is borrowed when you run the terminal operation. So a little bit confusing at first, but if you think about it for any length of time, you realize it's exactly what you want it to be. However, the default number of threads in the common fork join pool may be inadequate. And let's take a look at an example where that would be the case. So let's say, for sake of argument, that we're writing some kind of image processing or image crawler application, not unlike what you're doing for this class. And in this particular case, we're going to use the image stream gang example that I've talked about before. So this particular app is going to download and process images from remote websites. And process means apply image transforms, just like you do, and store them in the file system, just like you do, blah, blah, blah. And so what's happening here, as you can see, is we're going to have 10 images, but only 4 threads in our pool, which equate to 4 cores in the system. And what'll happen when we have more images to download than we have threads is we'll end up either underutilizing the number of available cores, and I'll explain why that is in a second, or we're going to end up perhaps with deadlock. Let's focus primarily, however, on the fact that you won't utilize the cores effectively. So the problem here is if we've got 10 images, but only 4 threads, then when those first 4 images are downloaded, if they happen to be large, each of those 4 threads will block. Now, when you block, you're basically putting the thread to sleep, and that thread can't make any further progress until the thread unblocks. And the thread would unblock when you're able to download the image. And if the images are large, then those threads could be sleeping for a fairly large amount of time, which will mean great underutilization of the number of cores. Because it turns out there, in fact, could be other things happening. We could be trying to download the other 6 images, but we've only got 4 threads. We've run out of units of logical computation in which to actually map down to the physical processing cores to do the work. So that's a problem. So what we really want here is to have at least as many threads in our pool as there are images to download, which could block. Well, there's a couple different ways to do this. One way to do this is to programmatically set the size of the common fork join pool when the program first starts to run, before it's actually any parallel streams have been created. And the way you can do this is by using a method that's defined on the system class called setProperty, and you basically give it a property name, a property string, which in this case is a rather verbose name, which is java.util.concurrent.forkjoinpool.common.parallelism. You can set that property to the number of desired threads. And it's a little hard to see because of where I am, but here we're going to set it to 8. Let's just say that we have a total of 8 cores on our machine. So we're going to have a pool of threads, and we could set those things explicitly. That works, but the problem is it's often hard to know how many threads we're going to need because we don't necessarily know in advance how many images we're going to be trying to download. Now, if you know you're going to download 8 images, then you can make 8 threads. But if you're going to download n images, much harder to do this because you don't know what n is until runtime. Another consequence of setting this flag is it affects all the parallel streams within a process. So this means that all the parallel streams will be sharing 8 threads in this particular case. And that could be overkill in some cases. Yet another problem is this property can be changed only before the common fork join pool is initialized. So this is what's sometimes called a lazy initialization or a first time in check. So the first time that we're going to be creating the common fork join pool, that's when the initialization gets done. And after it's initialized the first time, henceforth it's never checked again. So you can't set this parameter, you can't set this, or you can't configure this number any more than once. And even then you have to be very careful that it's before the stream starts to, any other stream starts to run. To avoid this problem, to work around this limitation with using the static mechanism, you can also use something else called a managed blocker. And managed blocker is an interface that's defined as of Java 8. And managed blockers can be used in conjunction with a few other mechanisms that are built into the common fork join pool to temporarily add worker threads to the common fork join pool. So you can kind of think of this as like seasonal help that's hired by Amazon or shopping malls or whatnot over the holidays when there's lots of people coming to shop. So you temporarily add extra threads. So in this particular case, what I'm showing here is if you're going to be doing blocking operations and you use the right mechanisms like the managed blocker interface and the managed block method on the common fork join pool, et cetera, et cetera, et cetera, then the system will temporarily and automatically create new threads on your behalf. And these threads are particularly useful for blocking I/O operations like downloading the images we talked about, and or various kinds of blocking synchronizers like, say, semaphores or condition variables and so on. This interface, this managed blocker interface, can only be used with the common fork join pool. You can't use it with a regular old fork join pool that you might create yourself. So it's really just intended to allow that common pool to expand. And what I don't really say here, but I'll just mention in passing, if threads are grown because you have blocking operations, but then your program goes into a period when it doesn't really have any blocking operations after a minute or so, then the common fork join pool will automatically terminate these temporarily created threads, kind of like Amazon or a shopping mall will let their seasonal workers go once the shopping rush for the holidays is over. You know, once it's January 2nd or whatever, probably even before then, but once the holiday rush is over, then they'll let those people go. So it's just a temporary boost meant to, I'll try to smooth out bursts of requests from clients that happen sporadically and not necessarily something you can easily anticipate the exact number in advance. So that's how you can configure and control the common fork join pool. The two ways to do things, of course, are through setting this property, which was that very long verbose string, but that comes with some strings attached, no pun intended, or you can use the managed blocker mechanism, which doesn't have strings attached. It has its own foibles, but in general, it's a much more effective way of scaling up the size of the common fork join pool automatically, and then having the system, the fork join pool framework, terminate those threads when they're not used after a period of time.